Hello, and welcome to video 2 of my 6-part video series on an overview of the AMC 10 math competition. My name is Michael Liu from Agora Math Circle, and today I will be covering Geometry 2. Specifically, we will be covering the area and circumference of a circle, arcs and sectors, circle theorems, quadrilaterals, polygons, and an example AMC 10 problem. So first, we'll do a quick review of the area and circumference of a circle. The formula for the area of a circle is pi r squared, where r is the radius, while the formula for the circumference of a circle is 2 pi r. And then, so for this circle here, we can see that's given that the radius is 4. In case you don't know, the radius is a line drawn from the center of the circle to a point on the circle. So you can see here the area is equal to pi times 4 squared, which is equal to 16 pi, and the circumference is equal to 2 times pi times 4, which is equal to 8 pi. In case you're wondering, pi is equal to roughly about 3.14, and there is a small chance that you'll need to know that for a few problems on AMC 10, but it is very, very unlikely. And I can't remember the last time I saw a problem where it was necessary to know the rough value of pi. Next, I'll be covering arcs and sectors. Arcs, they are a portion of the circle's circumference. So we can see here that if we were to say arc CB, that would be referring to this portion of the circle's circumference. Now sectors are a portion of the circle's area. So now the sector that corresponds to that arc would be CAB. It'd be this entire area here. So to find the length of an arc, we have this formula here. Alpha, which would be the central angle, divided by 180 degrees times pi times r. Now you notice that this is similar to the formula for the circumference of the circle. And we could actually write it out in an alternative form as alpha divided by 360 degrees times 2 pi r, which is just the circumference of the circle. Well, we know this is true because the arc is just a portion of the circle's circumference. Now the portion of the fraction of the circumference that the arc is equal to the degree of the central angle divided by 360 degrees. And in case you did not know, the degree of the entire circle is 360 degrees. So in this case, we can see that using this formula, we would plug it in. 120 degrees divided by 180 degrees times pi times 4 equals 2/3 times 4 pi, which is equal to 8 pi over 3. Now next we have the sector area formula, and as you can see similarly, it's just the central angle divided by 360 degrees times pi times r squared. So you can see here that the central angle is 120 degrees, which means that's 1/3 of the circle, and our plugging into our formula confirms this. So the radius is 4, we plug it in, it's 1/3 times the area of the circle, which is 16 pi over 3. Now we will be covering some theorems related to circles. Well, first we'll cover a few definitions. I already mentioned central angle earlier, but it's an angle that has a vertex on the center of the circle. And the vertex of the angle is the middle point and endpoints on the circumference. So if we had central angle CAB, A would be the vertex and C and B would be the endpoints. An inscribed angle is made of points on the circle's circumference. So we can see here CDB would be an example of an inscribed angle because all 3 points are on the circle's circumference. The measure of an inscribed angle is equal to 1/2 that of the central angle. So if we were given that the central angle is 120 degrees, the measure of the inscribed angle would be 60 degrees. There's a proof behind that, but I don't have enough time in this video to go over it. But I heavily encourage you to search up the proofs for this and all of the theorems I mentioned. This will help to deepen your understanding of the material. The measure of the arc is equal to the central angle. So arcs have a degree measure that's associated with them. So you see here the central angle is 120 degrees. So the measure of arc CB would be 120 degrees as well. And the measure of an inscribed angle with the same endpoints as another inscribed angle has the same measure. So you see here that we have inscribed angle CDB as well as CEB. Well, CDB is 60 degrees, and CEB, it would mean that CEB would also be 60 degrees. So now we have more circle theorems, and there's a lot of these. So now we'll go over chords. A chord of a circle is a line segment with endpoints on the circle's circumference. So you can see here that an example of a chord would be MN, 2 endpoints on the circle's circumference. There's also LK, same thing. So now we have a theorem. If two chords, NM and LK, intersect at point O, then LO times KO is equal to NO times NO. Well, these given values are just made up. They quite obviously do not fit the chords, but I'm just using these as an example. You can see here that MO, which is 8, times NO, which is 3, well, we multiply them, that's 24, and LO times OK would be equal to 24 as well. So a use for this theorem would be if, for example, we did not know what OK was. Well, you know that NM, NO times OM would be equal to 24, and you know that LO times OK would be equal to 24. So you'd see that OK would be equal to 24 divided by LO, which would be 4. So next, if an inscribed angle has endpoints on the diameter of the circle, and this is also known as an angle inscribed in a semicircle, the angle is a right angle. So you can see here that we have an angle inscribed here, and it kind of looks like a triangle inscribed in a semicircle, and this angle is a right angle. So we have even more. A tangent line to a circle touches the circle at one point only. So you can see here that RQ would be a tangent segment to the circle. It touches the circle at P only. And the point at which the tangent in the circle touch is called the point of tangency. So that would be point P right here. A line drawn from the center of the circle to the point of tangency is always perpendicular to the tangent line. So we see here the center of the circle is O. We draw a line from O to P, and we know for sure that it is perpendicular. So we can draw a right angle here. So next we'll be talking about secants. A secant of a circle has at least one endpoint outside of the circle and intersects the circle at 2 points. So you can see here that two examples of secants would be DG and DE. They each start outside the circle and they intersect the circle at 2 points. GH for DG and EF for DE. Tangent segments to a circle that have endpoints on the circle and the same endpoint outside the circle are equal. So we see here that DB is a tangent segment. It touches the circle at one point only. And DC is also a tangent segment. Touches the circle at one point only, and if we drew a line from A to C, it would be perpendicular. So knowing this, we can say that DC is equal to BC. A secant segment multiplied by the portion of the secant outside of the circle is equal to another secant segment with the same endpoints outside the circle multiplied by the portion of that secant segment outside the circle. Well, if you don't get what that means, basically, the secant segment outside the circle, well, let's say we have segment DG, the part of it outside the circle would be DH, and the secant itself would be DG, so we could say DG times DH, which is what this formula is talking about, this theorem, is equal to, well, we have another secant here, DE, the portion that's outside the circle is DF, so DH times DG is equal to DF times DE. They are also both equal to the squared length of a tangent that has the same endpoint outside the circle. So we can see that these four segments, they all have the same endpoint outside the circle. Two of them are secants, which we mentioned earlier, and the other two are tangents. So you can also say that DH times DG is equal to DF times DE, which is also equal to DB squared, which is also equal to DC squared. So these are all equal to each other. So this will be the last slide of circle theorems, I promise. The opposite angles of a quadrilateral inscribed in the circle, which means that all points of the quadrilateral are on the circle circumference. So you can see it demonstrated here with GHIF. This is a quadrilateral, and all 4 points are on the circle circumference. They are supplementary, which means they add up to 180 degrees. In case you didn't know, complementary angles add up to 90 degrees, and supplementary angles add up to 180 degrees. So we can see here that we have this quadrilateral that's inscribed in a circle, and we can know that opposite angles are supplementary. So we can say that the measure of angle HGF plus the measure of angle HIF is equal to 180 degrees, as well as the measure of angle GFI plus the measure of angle GHI is equal to 180 degrees. So the theorems that I've talked about are only a few of the many circle theorems that I have seen utilized most often. I heavily encourage you to find more on your own, as circle theorems are some of the most commonly used theorems in the geometry on the geometry problems in the AMC 10 tests. So next, I will be covering quadrilaterals. There are many kinds of quadrilaterals, but the ones I will be covering are trapezoids, parallelograms, rectangles, rhombi, and squares. A trapezoid is a parallelogram. A trapezoid is a quadrilateral with at least one pair of parallel sides. So you can see here that we have a trapezoid. It's quite obvious that the parallel sides are AB and DC. The area of a trapezoid is base 1 plus base 2 divided by 2 times h. So it doesn't matter which order you have the bases, but the bases are always going to be the parallel sides. So in this case, we could say that base 1 is DC and base 2 is AB. Isosceles trapezoids have two equal sides that are opposite each other. So this here is an isosceles trapezoid because these two sides are equal. So here we find the area of the trapezoid. Base 1 equals 5, base 2 equals 3, height equals 3. Area equals 5 plus 3 divided by 2 times 3. Well, that'd be 12. And one thing I'll mention, the median of a trapezoid, it's drawn from the middle of each leg. In case you didn't know, a leg is the non-parallel side. And its length is equal to this part of the area formula, base 1 plus base 2 divided by 2. So if I were to draw the median here, it would be right like that, assuming that this is equal to those two are the midpoints. And the length of that would be 4 because it's the average of the two bases. Next, I'll be going over parallelograms. A parallelogram is a quadrilateral with exactly two pairs of parallel sides. The formula for the area of a parallelogram is base times height. And any side will work for the base, but the height will always be perpendicular to the base. Opposite sides are equal and opposite angles are equal. So knowing this, we can say that BC and AD are equal, which means that AD is equal to 4. And we can also say that BA and CD are equal. And then using this, we can also say that angle B is equal to angle D, and angle A is equal to angle C. And then now using the formula, we can use 4 as the base and have 3 as the height, because this is perpendicular, or if this is, we knew this is perpendicular. So the area is 4 times 3, which is equal to 12. Now, if you somehow knew the side of this base, and then you drew a height from this base over here, you could also find the formula. You could also find the area that way. You can use any side of the parallelogram as a base. Next, I'll be going over rectangles. They are a special case of parallelograms with all of their angles being right angles. So if this is a right angle, we could know that that's a right angle, that's a right angle, and then these are all right angles. So the area is equal to base times height, or length times width. You can call it either way, it's the same thing. And diagonals are equal, and they bisect each other. So that means that this piece, this segment, is equal to this segment, which is also equal to this segment, which is equal to this segment. So now we have the application of the area formula. Base is 7, height is 4, the area is equal to 28. Next we have a rhombus. They are a special case of a parallelogram with all sides having equal lengths. So that would mean that BA is equal to AD, which is equal to DC, which is equal to CB. Their diagonals are perpendicular and bisect each other. They also bisect the angles of the rhombus. So that means is that they meet at a 90-degree angle. They bisect each other, so B to this point, we can just call it whatever we want. Let's say we can call it O. BO is equal to OD. CO is equal to OA. So, and they also bisect the angles of the rhombus. So CBD is equal to DBA, BAC is equal to CAD, and so on and so forth. So the area for this would still be base times height, but there's also another formula for the area, which is diagonal 1 times diagonal 2 divided by 2. This applies to all quadrilaterals whose diagonals are perpendicular. So even if I had a quadrilateral that wasn't a rhombus, say it looks like this, oh, that's a bad drawing, say it looks like this, well, that's very obviously not a rhombus, because its sides are quite obviously not equal, but this formula would still apply to it. So now we'll find the area of these rhombi. So first we can use the basic formula. So let's say we're given this rhombus with base is 5 and height of 4. It's just base times height, which is equal to 20. Now we'll use this new formula. Diagonal 1 times diagonal 2 divided by 2, which applies, as I said earlier, to all quadrilaterals who have perpendicular diagonals. So diagonal 1, well, we can see here that we're given half the diagonal. So to find the whole diagonal, we just multiply it by 2. And we know this since diagonals are bisect each other, so this length is equal to this length. So we get diagonal 1 is equal to 2 times 2, which equals 4. Diagonal 2, which is equal to 5 plus 5, which is 10. Or 5 times 2, it's the same thing. So then we get area equals 4 times 10 divided by 2, which is equal to 20. So you can notice that the reason why this area works is because each piece of the diagonal is a height or base of another triangle. So we can say that C to this point, this segment, is the base for both of these two triangles, and then BD is the combined height of both of these triangles. So what that means is C to this segment times BD times 1/2 is equal to these triangles, and the same thing for these triangles over here. If you don't understand that, you can search it up, and it doesn't really matter that much. Remembering the formula is more important than remembering the proofs. However, understanding the proofs will still always give you a better understanding of the material. Finally, we will cover a square. A square is a special case of a rectangle and rhombus where all sides are equal and all angles are right angles. So it's essentially a combination of the two. The formula for the area of a square is equal to one of its sides squared, since a side is equal to a base, and it's also equal to the height. So it's really the same as the rectangle formula or all other formulas. Its area can also be found using the diagonal squared divided by 2, since its diagonals are perpendicular. It inherits all properties from the square and rhombus, from the rectangle and rhombus. So here we can see that the side of the square is 5, so the area would be equal to 5 squared, which is equal to 25. Additionally, we could alternatively find that the diagonal is 5 radical 2, so then the area would be equal to 5 radical 2 squared over 2, which is equal to 50 over 2, which is equal to 25. And in case you're wondering how we found that that was 5 radical 2, we know that because it's also a rhombus, these angles are bisected. So since we know that these angles are bisected, and this is a 90-degree angle, this would be a 45-degree angle, and this would be a right triangle. And 45, 45, 90 right triangles have a property where the hypotenuse is equal to one of the legs times radical 2. So this diagonal would just be 5 radical 2. So to recap, if we had a 45, 45, 90 right triangle, and this was A, well, this would be A radical 2. So next we'll be covering polygons in general. There are two things about their angles that you need to know. The sum of all interior angles, and in case you're wondering what an interior angle is, it's basically these. It's the angles on the inside of the polygon. And this applies to all polygons, not just regular polygons. And in case you're wondering, a regular polygon is a polygon where all sides and all angles are equal. So an equilateral triangle would be a regular triangle, and a square would be a regular quadrilateral. So the sum of all interior angles is equal to 180 degrees times n minus 2. Well, if you're wondering why this formula works, well, think of the polygon with fewest sides, a triangle. Well, we know that it has 180 degrees. Well, if we add one more point, we get another triangle, so that adds another 180 degrees. And if we add another point, we get another triangle, which is another 180 degrees. So once we have the initial triangle, which is why we have the minus 2, because the first 2 points don't constitute a polygon, we need a third point for it to become a polygon. Each additional point adds an additional triangle, which would add an additional 180 degrees. So we see here we have a hexagon. Well, using the formula, we know that it has 6 sides. So 180 degrees times n minus 2, so that'd be 180 degrees times 6 minus 2. Well, that would be equal to 180 degrees times 4, which would be equal to 720 degrees. And we can verify this by seeing that we can split this into two triangles in a rectangle. Well, you see this is 180 degrees, this is 180 degrees, and this is 360 degrees. And if you want to find, since this is a regular hexagon, you could find the length of each interior angle by just dividing it by 6. So we would have 720 degrees divided by 6 is equal to 120 degrees. So if we were given that this is a regular polygon, which let's say we are, then we know that each side is 120 degrees. Now, the sum of all exterior angles of a polygon is 360 degrees. Now, if you're wondering what an exterior angle is, well, I can draw all of these out. And an exterior angle would be this, it would also be that. So basically, an exterior angle is when you extend a side out, and then it's the acute angle between the side and the rest of the figure, or it doesn't have to be acute. So if we added all of these up, we get 360 degrees. And since this is a regular polygon, all of these angles are equal, so we know each one would be 60 degrees. Now there's a basic area formula that applies only to regular polygons. That is 1/2 perimeter apothem. Well, perimeter is pretty self-explanatory. It's you just add up all of the sides. But if you don't know what apothem is, there's a point at the middle of the regular polygon, and you draw it down to a base. So this would be an apothem. Points from the middle drawn to a base, or one of the sides, and it must be perpendicular to the side. So now we'll use the area formula in an example. So we are seeing here that we're given a hexagon, and we are told that it's a regular hexagon. Well, we're already given the length of a side and the apothem, so this will be quite simple. So since it's a regular hexagon, all 6 sides will be equal. So that means that the perimeter would be equal to 6 times 10, which is equal to 60. And we're given our apothem is 5 radical 3. So we just plug it into our formula, and we get that the area is equal to 1/2 times 60 times 5 radical 3. And this is equal to 150 radical 3. So now we're given a more difficult example problem. It says, find the area of the regular hexagon. Well, to solve this, we're given a side, but we do not know the apothem, so we'll have to solve the apothem on our own. Well, we can notice that because each interior angle of a regular hexagon is 120 degrees, and drawing a line from a point to the center will bisect the angle. This will be 60 degrees. It's a property of hexagons, so we'll know that this is an equilateral triangle. And we also know that the apothem will bisect this side, so we know that this part is 4. So now we see that we have a 30, 60, 90 right triangle. In case you did not know, 30, 60, 90 right triangles have a property. So if we have this. So the two most important right triangles to remember in geometry are the 45, 45, 90 and the 30, 60, 90 right triangles. So if this side is 2a, then this side is a, and this side is a radical 3. So you can see here that this is just drawn out. So if we were to plug in the values from here, we'd see that this is 4, that would be 8, and this would be 4 radical 3. And this just so happens to be the apothem here. Is this triangle is just this triangle drawn there. So now we have our apothem, which is 4 radical 3. So we can plug it into our area formula, and we will get area equals 1/2 times 48 times 4, which would be equal to 96. So finally, we have our AMC 10 example problem. Now this problem is from the 2020 AMC 10B, and it's problem 14. It reads, as shown in the figure below, 6 semicircles lie in the interior of a regular hexagon with side length 2, so that the diameters of the semicircles coincide with the sides of the hexagon. What is the area of the shaded region inside the hexagon but outside all semicircles? If you want to try this problem yourself, pause the video now. If you want to receive a small hint, I will give you one in a few seconds. So the hint that I'll give you is that it's generally easier to find the area of the figure and then subtract the parts that's not shaded instead of finding the area that's shaded directly. Now, when you subtract the parts that's not shaded, be careful about over-subtracting overlapping parts. So give this problem a try and come back if you think you found the solution or if you've tried for a few minutes but couldn't make any progress. AMC 10 problems are difficult problems, so don't feel bad if you can't complete it. So now on to the solution. First, you can notice that we can easily find the area of the entire hexagon using the method shown earlier in the video. So using this method, we find that the area is equal to 6 radical 3, after we find that the apothem is radical 3 and the perimeter is 12. If you don't know how to finish this step, then rewind the video to review the usage of the 1/2 perimeter apothem formula. Then we could subtract the area of the non-shaded region from the hexagon to get the area of the shaded region. Well, at first the easiest way to do this seems like subtracting all of the semicircles. So we'll try that. So, well, the area of each semicircle is 1/2 the area of a normal circle, and the radius is 1 because, remember, this is the diameter, which is double the radius. So the radius is 1. So pi r squared, the area of a circle with radius 1 would be pi. The area of a semicircle, however, would be 1/2 pi. And we have 6 semicircles, so we have to subtract 3 pi. However, we also subtracted the overlapping area between the semicircles twice. In case you don't know which area I'm talking about, it's this right here. It's all of these. Well, that means that we need to add it back because if we subtract twice, then we've over-subtracted it. Well, how would we find the area of each of those overlapping areas? Well, to do that, we could split one of these in half, which as you can see we've done here. There is a way we could find, if we split this in half, we could find the area of one of the halves, which is what we'll try to do next. So to find the area of one of these halves, we form an equilateral triangle by drawing another line from the intersection point here to the middle of the hexagon right here. Well, after that, well, we know that this is 1 right here. So this is an equilateral triangle, so all these sides are 1. Well, how would you find this area of this half right here? Well, to find it, we could first find the area of this entire sector over here. And then we could find the shaded area right here, after we subtract the area of this triangle from the sector. Well, the area of the sector would be easy to find because it's just 1/6 of the entire area of the circle. So the area of the sector is 1/6 pi. Well, then we find the area of the triangle. There's a formula for the area of an equilateral triangle, which is s radical 3 over 4, where s is the side length. So you can see how it works there. If you don't remember that formula, you can also get it yourself. So if we have an equilateral triangle here with side length 1, 1, 1, we split it in half, we get 1/2. So this is very similar to how we found the apothem earlier. And this is radical 3 over 2. Well, then that would mean area would be equal to 1, which is the base, times radical 3 over 2 divided by 2. So that's because remember the area for the formula of the formula for the area of a triangle is 1/2 base height. So after that, we get radical 3 over 4. So if you don't remember this formula for the area of an equilateral triangle, you can also just find it yourself. Now this is one of the many reasons why it's very important to memorize the values for the 30, 60, 90 triangle. Those values come up very, very, very often. And also the 45, 45, 90 triangle. Well, after we get that, we can find the area of half of this overlap, which is just the area of the sector minus the area of this triangle. So the area of half the overlap would be 1/6 pi minus radical 3 over 4 pi. Or just radical 3 over 4, sorry. So we over-subtracted 6 of these overlaps, right? And this is 1/2. This area is 1/2 of the overlap. So we just add this area back to the hexagons 12 times, since there are 6 overlaps that were over-subtracted. And there we found was half an overlap. So that means that the shaded area would be equal to 6 radical 3 minus 3 pi, this is just the area of the hexagon minus the 6 semicircles. We have to add back 12 of the half the overlaps. So inside would be 1/6 pi minus radical 3 over 4. So then we expand, and we get 6 radical 3 minus 3 pi plus 2 pi minus 3 radical 3. And then we do our operations, and we will get 3 radical 3 minus pi. So this concludes our second video of this 6-part series, and I hope you have enjoyed watching this. Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!